Hello everyone, welcome to IS372, Information Management Research Methodology. In today's business world, organizations are surrounded by data. Whether we are making strategic decisions, analyzing markets, understanding customer behaviors, or improving internal operations, data is no longer just a record of what happened, it is a key resource that shapes what will happen next. In this course, we will explore multiple statistical methods that allow us to analyze data effectively and make better decisions in situations filled with uncertainty. We will not only learn how to perform statistical analysis, but more importantly, why these analytical approaches matter. Our goal is to connect data analysis to real business questions so that we can produce insights that are both meaningful and actionable. Throughout the course, we will work with different data sets in various business contexts, examining how statistical reasoning can support problem solving and guide decision making. This class is hands-on. You will learn the core theories of statistical analysis and then apply them directly using Python in the Google Colab environment. Through a combination of lectures, practical exercises, discussions, group projects, and assessments, you will develop the ability to analyze data step by step and communicate what the results mean. By the end of this course, you will be able to understand fundamental theories and techniques of statistical analysis, use Python to clean, analyze, and visualize data, apply analytical thinking to real-world business problems, and produce insights that support decision-making. You do not need to be a math expert or a programming specialist to begin. We will build skills gradually, focusing on clarity, intuition, and practical application. So bring your curiosity, engage with the data, and be ready to discover the stories that data can tell. I am excited to explore this journey with you. Let's get started. The first class is an overview and introduction of information management. First of all, let's understand what is information and what are related concepts. Let's check this image at first. This is Knowledge Management Cognitive Pyramid, also known as the DIKW model. This framework explains how organizations transform raw data into meaningful information, then into actionable knowledge, and ultimately into shared wisdom that guides strategic decision-making. As we move upward through the pyramid, the value and usefulness of what we understand increases. This process also changes how decisions are made, shifting from reacting to events at the lower levels to anticipating and planning proactively at the higher levels. Understanding this pyramid helps us recognize how data, analytics, experience, and judgment work together inside organizations. At the foundation of the pyramid is data management. Data is raw, unprocessed, and without interpretation. It may come from transactions, sensors, website clicks, financial logs, or medical equipment. Data alone does not tell us what to do. The essential task at this stage is ensuring that data is accurate, consistent, and accessible. For example, a retail system may record, "Product A sold 52 units today." That number is simply a fact with no meaning until we place it in context. Data management provides the infrastructure, quality control, and tools needed for later interpretation. Without reliable data at the foundation, the higher levels of the pyramid cannot function effectively. The next level is information management. At this stage, data is organized and contextualized so it becomes meaningful. For example, if we say, "Product A sells an average of 52 units per day, and we currently have 260 units in inventory," we now understand the situation more clearly. We know what the numbers represent and how they relate. Information provides structure, comparisons, timing, and descriptive meaning. It allows users to see patterns and trends. Information helps organizations respond to events more effectively, but it still does not tell us what actions to take. Knowledge emerges when we take information and combine it with experience, reasoning, and expertise. At this stage, we can make informed decisions. Continuing our retail example, we might conclude, if sales continue at this rate, inventory will run out in 5 days, so we should reorder now to avoid shortages. This is actionable knowledge. It helps individuals solve problems and take meaningful action. Knowledge shifts decision making from reaction to anticipation. It reduces risk because we not only recognize what is happening, but we also understand how to respond effectively. At the top of the pyramid is wisdom. Wisdom goes beyond understanding how to act. It explains why certain actions align best with long-term goals, values, and strategy. In the retail example, wisdom might lead a manager to order additional inventory ahead of a holiday season to improve customer satisfaction and avoid stockouts. Wisdom integrates experience, strategic thinking, and organizational priorities. It represents shared understanding that supports coordinated and forward-looking decisions. To summarize, the DIKW pyramid illustrates the journey from raw data to meaningful insight. Effective knowledge management requires reliable data systems, thoughtful information processes, skilled interpretation, and strategic judgment working together. Information management refers to the processes of collecting, organizing, storing, and sharing information so that it can be accessed and used effectively. The primary goal is to ensure that information remains accurate, reliable, and available whenever it is needed. Effective information management supports both daily operations and long-term strategic decisions. To achieve this, organizations use systems, tools, and procedures that manage information throughout its entire life cycle, from creation and active use to archiving or secure disposal. In the knowledge management pyramid, information management becomes important when raw data needs to be transformed into meaningful and interpretable content. Without this layer, organizations may have large amounts of data, but they would lack clarity and understanding. Information management bridges the gap between raw data and meaningful interpretation. For example, in a retail environment, a single number like 52 units sold today is only raw data. When information management processes compare that number with current inventory, historical sales trends, or seasonal demand, the data becomes useful information. By organizing the data into structured reports or dashboards, managers can understand the situation and make informed decisions. The same applies in healthcare. A patient's heart rate or temperature reading is simply a data point until it is organized into a chart compared with medical standards and stored securely in the patient's record. Once this happens, physicians can identify patterns, detect improvements or warning signs, and determine what actions are necessary. Across both examples, information management ensures that information is protected, traceable, consistent, and available to the right people at the right time. In summary, this layer plays a central role in the DIKW pyramid by enabling data to become understandable information and by providing the foundation needed for knowledge creation and effective decision making. Information management focuses on the systematic processes of collecting, organizing, storing, and sharing information so that organizations can operate effectively and make informed decisions. As organizations generate more data and rely on increasingly complex information systems, new challenges arise. For example, how should information be structured so it is easy to find? How can organizations protect information while still ensuring accessibility? How can information be interpreted accurately and applied meaningfully? These practical challenges inspire information management research. This research examines how information is handled throughout its entire life cycle and seeks to improve the methods, tools, and strategies used to manage it. It covers areas such as information retrieval, data management systems, content analysis, digital archiving, and knowledge management practices. The goal is not only to refine existing information processes, but also to discover innovative ways to use information for strategic insight, organizational learning, and more effective decision making. Information management research follows a structured yet iterative process. It begins with a practical problem. For example, a retail manager may notice that certain products run out unpredictably. This leads to the research question: when is the optimal time to reorder inventory? Next, the researcher reviews existing literature and constructs a theoretical explanation, such as using historical sales patterns to predict future inventory depletion. From this theory, a testable hypothesis is formed. For instance, if product A sells about 50 units per day and there are 260 units in stock, the hypothesis would be the product will be depleted in roughly 5 days. The key variables are then identified and measured using real data: daily sales volume, inventory levels, supplier lead time, and so on. After collecting the data, analysis and visualization reveal patterns and validate or adjust assumptions. A predictive model can then determine the best reorder point. If supplier delivery typically takes 4 days, the model may conclude that placing the order 5 days before stockout is optimal. Finally, the results feed back into theory. If the findings support the hypothesis, the theory becomes stronger. If they do not, the theory is revised. This cycle continues, ensuring that information management research evolves as technology, organizations, and environments change. In this course, we will use both statistical techniques and machine learning methods to analyze and manage information. Statistics focuses on collecting, analyzing, interpreting, and presenting data. Through statistical methods, we can identify patterns, understand trends, and make decisions that are supported by evidence. Machine learning builds on this by training computational models to automatically learn patterns from data and make predictions or decisions without needing explicit rules. These models are especially useful for tasks such as classification, clustering, recommendation, and predictive analytics. We will also study data mining, which involves exploring large data sets to uncover meaningful patterns and insights that may not be obvious at first glance. Data mining often combines statistical reasoning with machine learning techniques to support strategic decision-making in organizational settings. Together, these approaches will provide us with the analytical tools needed to manage information effectively and solve real-world problems. We begin with statistics because it provides the analytical foundation for transforming information into reliable and meaningful knowledge. Within the DKW framework, statistics plays a key role in moving from data to information and then from information to knowledge. When we convert raw data into information, descriptive statistics help us summarize, organize, and visualize data so it becomes interpretable. As we move further toward knowledge, inferential statistics becomes essential. Methods such as regression analysis and hypothesis testing allow us to evaluate relationships among variables, test assumptions, and draw conclusions that extend beyond the observed data. This ability to interpret patterns and make evidence-based conclusions allows statistical results to guide decision-making and practical problem-solving. Machine learning helps us handle larger and more complex datasets and supports the transition from knowledge to wisdom in the DIKW framework. As we move from data to information, machine learning algorithms can automate data processing and feature extraction, helping us structure data at scale. From information to knowledge, models such as clustering and classification identify hidden structures and recognize meaningful patterns. From knowledge to wisdom, advanced models like deep learning enable prediction and strategic decision-making, helping us anticipate outcomes and choose optimal actions. Data mining ties these ideas together. It combines statistical reasoning and machine learning techniques to uncover meaningful patterns in large datasets. Industries like retail, finance, and healthcare use data mining for customer behavior analysis, fraud detection, recommendation systems, and operational optimization. In short, machine learning and data mining extend our analytical capabilities and support prediction-driven strategy. Although statistical learning and machine learning are related, their goals differ. Statistical learning focuses on understanding how input variables relate to an outcome. It emphasizes interpretability, uncertainty, and theoretical reasoning. The goal is to develop a model that is meaningful and explainable. Machine learning, on the other hand, prioritizes predictive performance. It allows models to become more complex if doing so improves accuracy. Interpretability may be lower, but machine learning systems excel at recognizing patterns and making predictions in real-world environments. In this course, our primary emphasis will be on statistical learning because it builds strong conceptual understanding of how data relationships work. However, we will also introduce key machine learning concepts such as model construction, evaluation, and validation. This combined approach equips us to both understand data deeply and apply models effectively in practice. In this course, we will structure our learning using the CRISP-DM methodology, which stands for the Cross-Industry Standard Process for Data Mining. It is one of the most widely used frameworks in data analytics projects. CRISP-DM consists of 6 phases that form a continuous cycle. These phases are business understanding, data preparation, modeling, evaluation, and deployment. The sequence is not strictly linear. In practice, we often move back and forth between phases based on what we learn during the process. The outer circle of the model shows that data mining is iterative. Once a solution is deployed, new insights often lead to new questions and new rounds of analysis. Here is a brief overview of the key phases we will focus on in this course. First, business understanding involves clarifying the real problem and defining our data mining goals. Next, data preparation includes collecting, cleaning, selecting, and transforming data into a usable form. Then, in the modeling phase, we apply different analytical or machine learning techniques to build predictive or descriptive models. After that, during evaluation, we assess whether the model makes sense, whether it performs well, and most importantly, whether it addresses the business objective. Although deployment is important in real-world projects, this course will focus mainly on data understanding, data preparation, modeling, and evaluation. Together, these phases will guide us in turning raw data into meaningful insights and useful decision-making tools. In this course, we will use Python as our main tool for implementing data analysis and machine learning methods. Python is a high-level programming language that is known for being easy to read and simple to learn. Because of its clean and intuitive syntax, it is suitable for both beginners and experienced programmers. Python is also cross-platform, which means the same code can run on Windows, macOS, or Linux without modification. One of Python's greatest strengths is its large ecosystem of libraries. For example, Pandas and NumPy allow us to manage and analyze data efficiently. Scikit-learn and TensorFlow provide tools for machine learning and deep learning. Matplotlib and Seaborn help us create visualizations to better understand patterns and trends in the data. These libraries make Python a powerful tool for data analysis, information management, and research. We will also work with Google Colab, a free cloud-based platform where you can write and run Python code directly in your browser. There is no need to install software, and your work is saved online. Colab is widely used in data science and machine learning because it provides easy access to computing resources and supports collaboration. This will make it convenient for us to practice and experiment throughout the course.
Now, let's jump into our very first lab session, Python Fundamentals. This lab is designed to give you a foundational understanding of the core elements of Python programming, the building blocks we will use for all our data analysis projects. Before we dive into the code, let's quickly review how to navigate this environment. Google Colab, which is based on Jupyter Notebooks. The notebook is built from distinct cells. To structure your work, you will use 2 main types of cells, text and code. Click Add Text to add documentation, explanations, titles, and subtitles. For example, to create a main heading, use a single hashtag followed by a space. You can format the text with bolding, italics, or lists in the text editor pane. Use 2 or 3 hashtags for subheadings. Click Add Code to add cells where you can actually write and run your Python code. To execute the code in a cell, simply press the Run button, the triangle icon. Finally, let's talk about saving. By default, all your changes in this Colab notebook are automatically saved to your Google Drive within a folder named Colab Notebooks. If you want to move this file to a specific course folder, and then use the Move option to put it exactly where you need it. Now that we know how to navigate the notebook, let's start with a concept critical to Python: indentation. Unlike many other languages where spacing is just for readability, in Python, indentation is essential. It's how the language defines a block of code. For example, the print statement here is indented 2 spaces, telling Python it belongs to the if statement above it. If you skip this indentation, Python throws an error. Also, within the same block, you must use the same number of spaces or you'll get an indentation error. This strict rule ensures our code is always clean and readable. Next, let's look at comments. Comments are text that Python ignores during execution. We use them to explain our code, make it more readable, or temporarily stop a line of code from running while we test. A comment always starts with the hash symbol. You can put a comment at the end of a line or use hash on multiple lines for longer explanations. Alternatively, you can use triple quotes to create a multi-line string literal, which Python ignores if it's not assigned to a variable, effectively acting as a multi-line comment. Moving on to variables. Variables are simply containers for storing data values. The great thing about Python is that you don't need a special command to declare a variable. A variable is created the moment you assign a value to it. Look closely at this example. X is assigned to the number 5, making it an integer, and Y is assigned the text John, making it a string. Python uses the equal sign, the assignment operator, to link the value on the right to the variable name on the left. The print function then retrieves and displays those stored values. Variables are dynamically typed, meaning a variable can even change its data type after it's been set. Here, X starts as an integer, but is immediately reassigned to be a string. Python handles this without issue. Understanding data types is key for working with data. Python has several categories of built-in types. The main ones we'll use are numeric, int, float, complex, text, str, and the essential sequence collection types. You can always check the type of a variable using the type outside function. Let's see this example we have before. When we assign 4 to x, the x is of type int. Then we dynamically assign the string Sally to x, which changed the type of x to string. This example not only shows how types of variables can be dynamically changed, but also shows how you can use the type function to check the types of variables. You can also explicitly set the type using constructor functions. For example, when we assign 5 to x, x is type of int. But we can retype it using a string function to make it a string type. Same thing, we can use int and float functions to retype the variables. Now let's check the different types in numbers. Python supports three main numeric types: int, float, and complex. We only focus on int and float. A numeric variable is created when a number is assigned to it. An integer is a whole number, either positive or negative without decimals. Integers in Python have unlimited length, which means they can grow as large as memory allows. A float is a number that contains one or more decimal places. You can convert from one type to another with the int and float functions. A string is a sequence of characters enclosed in either single quotes or double quotes. For example, hello and hello represent the same string. You can print a string using the print function. You can use quotes inside a string as long as they don't match the quotes surrounding the string. A string can be assigned to a variable using the assignment operator. To create a multi-line string, place the text inside 3 single or 3 double quotation marks. An F string allows you to insert variables or expressions directly into a string. Place an F before the opening quote and include expressions inside curly braces. For example, when we assign variable A with hello, we can print hello world using F string with variable A inside of the quote. So it will print the value of variable A and the world. Now let's see another example. Assume we assign Alice to a variable name and 30 to variable age. We can use F string to print both variables in one sentence, like this. The benefit is, if we want to change the name and age, we don't need to change the F string anymore. We just need to reassign the value of variables, and the result will show whatever values we assign to the variables. Python pursuit type provides several built-in data types that are essential for storing and organizing data during programming and data analysis. 4 of the most commonly used built-in collections are list, tuple, set, and dictionary. These data types play an important role in analytical tasks because they allow us to structure data, manipulate values efficiently, and perform operations that support reasoning and decision-making. In this course, we will begin by introducing what each type is and how it behaves. You will learn how to apply these data structures in real analytical scenarios as the course progresses. A list is a built-in data type used to store multiple items in a single variable. Lists are written using square brackets. List items are ordered, meaning each item has a defined position in the sequence. They are also changeable, meaning elements can be modified after the list is created. Lists allow duplicate values. Each item is indexed, with the first item located at index 0, the second at index 1, and so on. Negative indexes can be used to access items from the end of the list, where -1 refers to the last item. The number of items in a list can be determined using the len function. A specific section of a list can be accessed using a range of index values, which returns a new list containing the selected items. For example, the 0 to 2 means this subsection starts at index 0, the first item, and ends at index 2, the third item. But remember, the third item is not included. As a result, this returns the first 2 items in the list. Here, we leave the start index empty. When we do that, Python automatically starts at index 0. So this list, :2, also returns the first 2 items. It's the same as the previous example. In this slice, we start at index 1 and end at index 3, not included. That means Python returns the item at index 1 and the item at index 2. So this list 1 to 3 gives us the second and third items in the list. In this example, we start at index 1, but we leave the end index empty. When you leave the end index out, Python automatically goes all the way to the end of the list. So subsection returns everything from the second item all the way to the last item.
Lists may also be created using the list constructor. Lists can be sorted either alphabetically or numerically, and sorting can be reversed when needed by specifying reverse equal sign true. Python also provides methods such as the plus operator, append, or extend to add all items from one list to another. Even though they sound similar, they behave very differently. When you use plus between two lists, Python creates a brand new list that combines both lists. So use plus when you want a new combined list without modifying the original ones. The append method adds a single item to the end of a list. If that one item happens to be another list, then the whole list is added as one element. Finally, extend does the opposite of append for lists. Instead of adding the whole list as one item, it takes each item from the second list and adds it individually to the first. Lists of strings can be combined into a single string using the join loading method, which inserts a chosen separator between elements. A tuple is another type of collection used to store multiple items in a single variable. Tuples are written with round brackets. Unlike lists, tuples are unchangeable. Once a tuple is created, its items cannot be modified. Tuples maintain order and can contain duplicate values, similar to lists. Their unchangeable nature makes tuples useful when data must remain constant throughout the program. A set is a collection used to store multiple items in a single variable. Sets are written using curly braces. A set is unordered, meaning the order of items is not fixed and may vary. Sets are also unindexed, so items cannot be accessed by position. Sets do not allow duplicate values. If duplicate items are included, Python will automatically remove them. Sets are often used when determining membership or removing duplicate items from data. Python provides operations for combining sets while ensuring that no duplicates are introduced. The union operator method returns a new set with all items from both sets. The update method inserts all items from one set into another. The update changes the original set and does not return a new set. The intersection method and operator will return a new set that only contains the items that are present in both sets. The difference method per inch. Operator will return a new set that will contain only the items from the first set that are not present in the other set. A dictionary stores data in key-value pairs. Dictionaries are written using curly braces, with each item consisting of a key followed by a value. A dictionary is ordered and changeable, and it does not allow duplicate keys. Keys act as identifiers for accessing the corresponding value. Dictionaries are commonly used when information needs to be retrieved using meaningful labels rather than numeric indices. Here is the difference between the four built-in data types. They differ mainly in order, mutability, and how they store data. A list is ordered and mutable, allowing duplicates. A tuple is also ordered but immutable, meaning its values cannot change. A set is unordered, mutable, and contains only unique items with no duplicates. And a dictionary is ordered and immutable, but it stores data as key-value pairs rather than single values. A data frame is a tabular data structure provided by the Pandas library. It is similar to a spreadsheet or a relational database table. The data frame consists of rows and columns, where each column has a label and holds values of a particular data type. Data frames are widely used in data analysis
because they make it easy to organize, filter, clean, analyze, summarize, and visualize data efficiently. They support operations such as sorting, grouping, merging, and statistical computation, which are essential in information management and analytics workflows. A dictionary in Python is well suited for representing record-style data that can be converted into a data frame. Dictionaries become especially powerful when combined with lists to create data frames. Pandas allows us to convert structured data into tables with a list of dictionaries. Each dictionary represents one row. First, we need to import the Pandas library, which is a powerful tool for working with tabular data in Python. This lets us use Pandas functions like DataFrame. Next, we create a list called records. Each item in this list is a dictionary where the keys are column names and the values are the data. Each dictionary represents one row in our table. The keys brand, model, and year will become the column names in the data frame. The values are the actual data for each row. Then we use the PD data frame function to turn our list of dictionaries into a data frame. PD data frame record reads each dictionary as a row. The column names are automatically taken from the dictionary keys. Finally, we can print the data frame to see it in a table format. Using a list of dictionaries is convenient because it mirrors real-world data. Each record has the same fields. Pandas can automatically convert this structure into a data frame, which makes it easy to analyze, filter, or manipulate tabular data in Python. When working with data frames, we often need to access specific rows and columns. Pandas provides two key indexing methods for this purpose. Log means labels, which are row names and column names. For example, if we want to get the model of the second car, we can use log1 model. Here, 1 is the raw label. By default, Pandas automatically assigns integer labels starting from 0 if no custom index is provided. So 0 is the first row, 1 is the second, and 2 is the third. Then model is the column name. If we want more than one column for a specific row, we pass a list of column names, like both brand and the year, which is a list of columns we want to retrieve. Someone might get confused why log is using labels and names, but there are index numbers here in the code. Even if it looks like an index, it's technically a label, which by default is the same as the row number. If you set a custom index, log will use that custom label instead. So here, the 1 and the model selects row labeled 1 and column model, not necessarily the first row. It's based on the label. And alog are integer positions, which are row index numbers and column index numbers. We can select the value in row 0, column 2 to retrieve the year of the third car. Now, for operators, which are used to perform operations on values and variables, we have three main categories. Arithmetic. Operators are for basic math: addition, subtraction, multiplication, and division. They also include modulus, exponentiation, and floor division. Assignment operators are used to assign values to variables. The shorthand operators like plus equal and minus equal are very common. Simplifying x equals x plus 3 to just x plus equals sine 3. Comparison operators are used to compare two values, returning either true or false. This includes equality, which is two equal signs, inequality, and the greater or less than checks. Finally, let's look at if-else statements, which use those comparison operators to control the flow of your program. An if statement tests a condition. Python supports the usual logical conditions from mathematics. In the following example, we use two variables, a and b, which are used as part of the if statement to test whether b is greater than a. As A is 33 and B is 200, we know that 200 is greater than 33, and so we print to the screen that B is greater than A. If the initial if condition is false, Python moves to the elif, short for else if, to test another condition. If none of the preceding conditions are true, the code falls back to the final else block. Back to our assignment, we can add if and else statement. Now, since 200 is greater than 33, we print to the screen that B is greater than A. If we change A to 200, B to 33, then the result changes to B is smaller than A. Because the initial condition is false, and if condition is also false, it has to go to the else condition. At last, we can change both A and B to 200, then the if condition is true, so that the execution stops and Python print B and A are equal. We can also combine multiple conditions using logical operators like AND, where both sides must be true, and OR, where at least one side must be true. In another example, if the condition is true, the assignment operator can even update the variable. At last, you can even create nested if statements by placing an if statement inside another if or else block. In this example, Python checks the outer if at first. Since x is 41, this condition is true, so Python executes the code inside this block to print above 10. And inside that first block, we have another if statement. Because 41 is also greater than 20, this condition is true, so the program prints and also above 20. Thus, a nested if statement is simple. It is just an if block inside another if block. It allows you to check multiple related conditions. Each condition gets evaluated only if the previous one is true. Now, this is the main content of section 1 of IS372. It is your time to do your tasks in discussion, quiz, and assignment. Good luck.